Today our speaker is Haibo, and Haibo is assistant professor of Xi'an University of Post and Telecommunication from 2010, here in which he became assistant professor after he finished the PhD at Lanzhou University. Yes, the pronunciation is. And he's working in core atoms and Bose-Einstein condensate, mainly in their dynamical features and critical phenomena. And during the last months, starting from October 2014, he is visiting the group of Juliá-Díaz and Artur Pols at the University of Barcelona. Today he will tell us about synchronization measure. And please, just.
First, I want to thank Roberto to invite me to give this seminar, also invite me to visit her group. And the title of my talk is Mirror Synchronization. Mirror Synchronization goes quantum. Sorry, the boundaries. Sorry.
No, I see.
Let's just continue. And first, the contents of my talk include those parts, and I give some background of the topic that I'm talking about, because this is not familiar with the audience. And the first is what we are telling, this mirror synchronization. Actually, when we talk about mirror synchronization, it's completely different thing compared with synchronization measure. This is something different. And also that our system, this is a system that from the electrical gases. This is my background. And we use this system to do the research on this mirror synchronization. So it's discipline research. And before we go into the quantum, first I will present our research on the classical mirror synchronization, and then we will go to the quantum. So there is another comparison group of this research, and at last is the conclusion. And first, what is mirror synchronization? And mirror synchronization is that stands for the collective dynamics that's shown in a non-dissipative coupled Hamiltonian system. So it must be the Hamiltonian system. So Hamiltonian system actually means it must be non-dissipative. And for this concept, it is characterized by the invariant measure of the phase space domain of subsystems. And here is the example that is showing this picture. And also this concept is introduced in 1999. So relatively it is a new concept, but not received much attention since this concept comes out. And here we consider this Hamiltonian system, and it's a two-coupled system. And this is H1 and this is H2. For each of the Hamiltonian system is a 1 degree of freedom system. So it's described by the conjugate variable Q1 and P1 and Q2. And also there must be some coupling because we want to show the collective dynamics of the synchronization. And this is the general thing that we can write for the coupling term. And also there's another important coefficient in this mirror synchronization scenario is this C. This C stands for the coupling strength. So here it shows what is mirror synchronization in these figures. And there are 4 different figures. And these 4 different figures correspond to a different C. So now we are tuning this coupling strings. And at first, it's from the zero coupling strings. And with zero coupling strings, what we are showing here is a phase space picture. And this phase space picture is showing by the P1 and Q1 and P2 and Q2. Actually, this phase space picture is an overlap. It's overlap for the two Hamiltonian system. And those, at first, with zero coupling, we know that each of the subsystems actually is energy conserved. So we see the contours. Actually, this contour is energy contour. means that this along this line is all energy conserved. And now we will show the effect of this coupling. And by tuning this coupling to a non-zero value, and you will notice that this phase space dynamics, this control is replaced by the phase space domains. The black one is for one of the subsystem H1, and the green one is for the H2. So there are two subsystems. And what is interesting is that when we tune in these coupling strings, you will notice those two phase space domains is completely separate. But when we tune in these coupling strings, and you will notice these two phase space domains is approaching each other. And this approaching is actually the boundaries of this boundary here, and also this boundary is getting close to each other. And until it's getting almost close touch, as what we're showing here is close, almost close touch. And when it's really getting touched, then suddenly there will be a sudden of this phase space domains. And this sudden change will lead to this kind of picture. And this kind of picture, we see the phase space domains for the two subsystems, these two Hamiltonian systems, is become identical. So the area is the same. And also those authors is arguing it is not the area that we see here is the same. And it is also the phase space domains. Now it has invariant measure. So after noticing that, and they define this kind of thing as Mayer synchronization. So Mayer synchronization means that in the phase space domains, we have complete overlapped phase space domains. So this is the way that we see whether it is Mayer synchronization or not.
May I ask why the terminology synchronization is used for that? Because synchronization is a temporal feature and you refer just to an area of a phase space.
Yes, that I'm going next slide.
Your interaction Hamiltonian is called H12. Does it mean that it's directional, or there's no assumption?
Because there's no assumption.
General.
It's very general.
And what are the colors?
The color is for the different spaces, and also this red line is a reference. So next I will talk the difference of Mayer synchronization, why this thing we call it Mayer synchronization and things like that. And this is a comparison for what we call Mayer synchronization and what we know for the larger audiences. For synchronization is the spontaneous synchronization. And the difference for Mayer synchronization and the spontaneous synchronization is in the following. And the first one is Mayer synchronization actually is a deterministic synchronization. So there is no transit time to reach this synchronization. It's determined by these coupling strings, as we've already said, is a critical thing that is happening in the phase space domains. And this is the first thing. And the second thing is that it's quite strange that this kind of synchronization is defined on the spatial coincidence, but not rather on the time coincidence, like the temporal evolution. So this is just its definition. And the third one is it is non-dissipative, whereas for the spontaneous synchronization, we always have some dissipation. And to make the temporal evolution is the same, identical or synchronized in some sense. So they are very different.
Could you define deterministic synchronization? I mean, if you have deterministic dynamical systems, then what is non-deterministic synchronization?
For this deterministic, it's true that for all the Hamiltonian system, the dynamics is deterministic. So this is where the deterministic that comes from. And this concept relies on this Hamiltonian system. So this is a consequence that when we choose this system. And for the non-deterministic, actually, for spontaneous, I mean, it's not deterministic. It's always determined by something. And this is some very brief introduction of the concept and how we define this Mayer synchronization. And this is the way to show it. And next is our model system. And this model system is from the edge-cooled gases. It's another from another field. First, I will tell you what is bosonic-Josephson junction. Then I will go through the model system that I use. And for the bosonic-Josephson junction, actually this concept is defined by the analogy of the Josephson effects with superconductors. And we all know that for superconductors, we separate two superconductors by an insulator, and this insulator can be viewed as a barrier, and you will detect the current in between those superconductors, and this is what we know for the Josephson effects in the superconductor. And in analogy with Bose-Einstein condensate, this is edge-cooled gases. When we trap, those are atoms, but it is in a Bose-Einstein condensate state, and here is a double potential. And this double potential is used because now we can see this thing as a barrier as that one. And also there are more similarities. It's because for the Bose-Einstein condensate and also for the superconductor, the quantum state can all be described by the same number. And this is the same number that we write. It's a microscopic quantum phenomenon. So this is analogy. And also, it is first pointed out in 1986 by this author. Actually, for the atoms in the Bose-Einstein condensate state, this tunneling is a Josephson effect. So this is how we call it bosonic-Josephson junction, because we use Bose-Einstein condensate. And for what the basic physics that we are studying, before we are going to a more complicated system, we should first start it with a single one. This single one is what we call a single species VGG. And the single species VGG means that here we only have one kind of atoms that in the Bose-Einstein condensate. Whereas actually to creating this Bose-Einstein condensate, we can use different atoms. So it can be different components comprised of this Bose-Einstein condensate. So this is a simple case that we're considering. And to describe this kind of physics, we can use a two-mode model to describe the Josephson effects in the bosonic-Josephson junction. And this two-mode model is very simple to explain because it's very simple as it writes. And the first term, this V term, and also this operator term is in the second quantization. And this thing means that the tunneling. And you will notice that it's an annihilation of the atoms in the R well. So it is in the right well, it's disappear one atoms. And at the same time, it is created another atoms in the left well, and vice versa. So this is the tunneling term. And this V is a coefficient that is telling us how strong this tunneling effect is. And the second term is this U term. And this U term is a full operator term. And this term describes the interaction term. And this interaction is from the interacting of atoms. So this way is telling us how large the interaction between the atoms are. And what is amazing for these edge-cooled gases, you may have heard of such advertisement before, is that for this U and for this V, it can be all tuned in the experiment. So we can tune in these coefficients in the experiment. And the most simple theory to describe this two-mode model is what we call the classical theory. And this classical theory is introduced in 1997. So it's quite new because the Bose-Einstein condensate is created in the experiment in 1995. So this research is 2 years later. And what is a classical theory is that we suppose that for this kind of quantum state, it is always remain condensed. So we have this phi BEC state. And this phi BEC state is actually a coherent state that we can write down like this one in the two mode. And then we calculate the expectation values of this H, and we can get something classical. And this is what we get. This H is a classical Hamiltonian description of the quantum model. And to tell the H, and you will notice the coefficient is still there, and this U and this way, so this is for the interaction term, and this is the tunneling term. But here, there are two conjugate variables for this Hamiltonian. And these conjugate variables, one is S, and another one is theta. It's apparently not here, so it's introduced later. And it is introduced as a population imbalance S, and the relative phase. The population imbalances tell us how different the particle numbers in the left well and in the right well. So it's an imbalance. And the relative phase is for the Bose-Einstein condensate, because Bose-Einstein condensate have a phase. So there should be the phase difference of the two condensed system. And also for the H Hamiltonian is very simple one, because it's a one degree of freedom system. This S and theta is like Q and P to describe the single system. And what is most interesting coming from the above story for a single species VGG is what we call for the self-trapping. And the self-trapping is another effect that besides for the Josephson effects. The Josephson effect is shown here. I've mentioned before that actually the tunneling between those two wells is a Josephson effect. So in the experiment, this is some experiment data, and this is temporal evolution. And this temporal evolution is for the population imbalance. Is that the atoms actually is tunneling here, and also this is some wave function is shown here, and you will notice this wave function is changing initially, which represents the dynamics of the system. And this is for the Josephson oscillations in the experiment. And is this self-trapping? It is also produced by this experiment. And you will see what is self-tracking is that it's for this temporal evolution of the population imbalance, it starts from here and it's not tunneling so much. So it is not tunneling. It's like all the atoms is trapped in a single web. So this is what we call for the self-trapping. And the prediction of this self-trapping state is made by this paper for the classical theory. And also the experiment data that I show here is from this paper, is from 2005. So after these 8 years, and they produced this, they proved that this state for the self-trapping. And this is already the biggest story for the physics study of this single species VGG. And now we have to make our connections to the topics that I want to discuss. And the connection is here. This one is also produced by the experiment. What they did is they map this kind of dynamics to a phase space. And here you see this phase space, and you will notice the topology of this phase space. And you have area of this kind of circles and another one. And these two different topologies, this represents for the Josephson oscillation of this kind, is these oscillations. And for the self-trapping, it's shown here. So this axis is this one is the population imbalance, and this one is the phase difference. So it's a classical phase space. And those one are the experiment data. So what we want to use is here we have a 1 degree of freedom classical system. So we already have this one. It's a control. So here we have one control. And what we need more is another control. So we need a coupled classical system. And how to make that happen is that we must go to a more complicated system than a single species VGG. And this system is what we call a two species VGG. And a two species VGG is not so different compared with a single species VGG. It's just we add another atom B. And also this atom B is also Bose-Einstein condensate. And the two-mode model to describe a two species VGG is very similar also. And here we see these terms in the second quantization, this quantum model. And we have these U terms, the interaction, but for A. And we have this UB is for the B interaction. And also the tunneling term for the A atoms and tunneling term for the B atoms. And what's more, and this is also very crucial is the last term. The last term is a for operator term, so it's an interaction term. And this interaction term is this UAV. This UAV, you will notice that here is all L. It means the interaction inside of left wheel. And also it has interactions in the right wheel. But this interaction is between different kind of atoms. So it's interaction of A atoms with B atoms. So this is the two-mode model that we will use. And for that, we can also do a classical theory as before. And now the Bose-Einstein condensate is more complicated because we have two different kinds of Bose-Einstein condensate. It's the two spaces. So we write this one, and we can derive another classical Hamiltonian as before. And this time, this H is, of course, it should be complicated because we have two different kinds of atoms to describe. And here it is. And we have this VA term, it means the tangent term for the A atoms, and VB for the B atoms, and UA and UB, and UAB is the interaction term. And this is interaction of the spaces A and interactions of the spaces B and interaction between spaces A and spaces B. So we have it, and also we have to notice that this Hamiltonian now is a 2 degree of freedom. So it's a 4-dimensional system. And this 4-dimensional is this population balance for A and for B, and relative phase for A and for B. So this kind of classical theory is first derived in 2002. So, to start is the Hamiltonian dynamics, and what we have to do is to show the Hamiltonian equations. Sorry for this thing. It's these equations, and we solve this equation, we will get the classical dynamics in a deterministic way.
These are just S dot, Q dot.
Yeah. It should be all the dots.
And also Q is the theta before is the relative angles.
Oh yeah. This should be theta. Theta A, and this should be theta B with some showing problem. Now we have our theory, and we have a 2 degree of freedom system, so we can start our stories. And where we started is that we read the Hamiltonian, this classical Hamiltonian for two spaces BGG problem as H equals to HA plus HB and plus HAB. You might remember that when I first introduced mirror synchronization, it is written as H1 plus H1. So it's very similar in the formulations. But now we have this H. Is a 1 degree of freedom Hamiltonian system. Is this one. And this Hamiltonian actually is a single species BGG Hamiltonian system that we've introduced before. And the coupling term is this HAD term. You will notice this coupling term is very simple. It's a linear coupling. And also the coupling strings now is this UEV. And this UEV is the interaction term. So in principle, we have two different interactions. And in the experiment, they can both be tuned. Is for the repulsive interaction and for the attractive interaction. So this UEV, in principle, it can be negative and it can be positive both. And this two spaces BGG, now you will notice that it's like two coupled single BGGs.
How do they change the sign?
It's for the positive is for the repulsive, and negative is for
in the experiment.
In the experiment, they have a so-called Fishbach resonance. It's a technique that can change from repulsive or attractive. So this thing can be done. Okay. Now we have our model system. It's a classical model system, and it's a two-coupled classical Hamiltonian system. And now we can start our stories for the classical mirror synchronization. And this is the first part before we are going to the quantum. And to present our result, we have to tell you that the parameters in the calculations. And the first, and it is an important thing that keep in mind, is that for mirror synchronization, we have to have identical systems. So to have identical system, this VA should be equal to VB, and UA should be equal to UB. And also here we choose UA equals to UB equals to 1.2. And we choose this value because this value is the most interesting physical regime that we can study, is the Josephson regime. Besides this Josephson regime, there's another regime which we call gravity regime, this Fock regime. So there are 3 different kind of physical regimes that we can do our study. And to show the mirror synchronization, the most important thing and the only parameter that we should tune is this coupling strings, this UED. So next is our result for the classical mirror synchronization. And this is also the phase-space dynamics that we showed before. And start from 0. So it's a 0 coupling, this UED. And by tuning it, by increasing it, you will notice these contours will be replaced by the phase-space domains that we show here. And by keeping these coupling strings, these phase-space domains will be getting close to each other. And this is already the critical point before this phase transition. And when it increases a little bit, the two phases will be completely the same. So this kind of state is what we call mirror synchronization. And also, if we keep increasing these coupling strings, this phase-space domains is all look the same as this one. So it's some kind of synchronization state that we find, and it is also a critical thing that this is a critical point that we can show.
The point where this happens depends on the initial separation between the systems.
Yes.
So that is set by the initial condition, I guess, because it says what's the amplitude of the orbits is given by the initial number of particles that you have for each system. No?
Yes, that's true. And this is the initial condition that we choose.
So if you increase, say, the difference, say 0.1 and 0.5, then the critical value is a little bit bigger.
Yes, we change. And this is for the phase-space domains, and some people will argue that this is completely not synchronization because we cannot see the temporal evolution. And so here I show the temporal evolution. And here what I show is for the most explored in the experiment is the imbalance, the population imbalance. This is population imbalance for A, and this is for population imbalance for B. And those two figures is choose for two sets of the coupling strings. One is for the non-mirror synchronized state. So its UEV relatively small, and also another one is for the mirror synchronized. Its UEV is relatively large. And here, actually, you cannot really say that it is in phase or antiphase, because there's no in phase and antiphase in mirror synchronization in this temporal evolution. But anyway, you will notice this kind of mirror synchronization is more collective compared with this one. Because you can see it's like a delayed effect is happening here. You shifted this evolution is getting here, it's maybe completely overlap. But it is not completely overlap anymore. But anyway, this is a temporal evolution, and from here we cannot really say the synchronized dynamics. So we choose another way to show the synchronized dynamics. Is that here we calculate for the phase dynamics. And this one is what we define as a phase. It is a Euro way that we define a phase in a phase space. And this is our conjugate variable, this theta and s. And this phi have two systems, so we have defined two different phases. And what we did is to calculate the phase difference of the two spaces. And this is the result that we get. And there are different curves. This different curve is we get different curve by choosing different coupling strings. So here we choose 5 different coupling strings. And this one is very small and is getting increasing. And for very small coupling strings, you will notice it's a rounding phase. So it's not phase lock. And by increasing these coupling strings, this slope of this curve is getting smaller, and until it's this thing, MS transition. So from this one, this value of coupling strings, and to this value of coupling strings, you will notice it's a phase lock transition. It's happening here. But anyway, this phase locking is a non-strict phase locking because it is not locked to a fixed value of this this delta phi. So anyhow, it is a phase locking phenomenon that we can show by calculating the phase dynamics. The most important feature for the mirror synchronization is another thing that we call energy characteristics that for mirror synchronization. And here what we calculate energies for each of the subsystems. So we have two different spaces, and each the spaces has its own energy. And here the different lines is for the different spaces, the energy of spaces. And those three curves correspond to these three situations. This is the phase space domains. And this is corresponding to these energy evolutions. And you will notice what is happening is that when the phase boundaries is getting close to each other, this minimum value of this curve and the maximum value of this curve is getting close to each other also. And also this critical point, you will see this getting almost close touch here. And then suddenly this MS transition is the transition of energies to this kind of situation, is fully exchanged. So from this energy calculation, we are calling this kind of transition as a demixing to mixing transition behavior. And this energy characteristic is the most important feature that shows in the mirror synchronization. And by using this energy calculation, we can even show the MS transitions here. And what we are plotting here is the averaged energies. The averaged energy, of course, for this one is might be this value. It's averaged, and this one is averaged. And different colors is for the different system. So with this x-axis is for the coupling strings. So at first, when the coupling strings is very small, it's not mirror synchronized, so you will say they are separate. But when it reaches mirror synchronization, they will be the same. And here the inside is showing the two scenarios of the energy evolution. So this one is corresponding to these coupling strings and it's this thing. And this one is corresponding to this one. So by using this average energy calculation, we can show the critical behavior of this MS transition. And this is the critical value for this transition point. And also, we can show the dynamical mechanism behind this MS transition. Because what we say is the phase space domains, suddenly they become the same. And what is behind it is some critical behavior that we can show by doing a Pankara section analysis. And here, basically what we are telling is that for different colors, this black one and this gray one is for when they are separate, they are not mirror synchronized. When they are overlapped, it is already mirror synchronized. So here is the separation part, and this is the separatics. So at first, when we're approaching this separatics, and when we cross this separatics, it reaches this mirror synchronization. So what is behind this sudden change of the phase space is we cross this separatics. And so what is behind this thing is what we call the separative crossing behavior. And I didn't emphasize before, because for the classical theory for a single species BGG, actually from the Josephson oscillation to the set traveling, and this separative crossing is also the dynamical mechanism behind this phase transition behavior. And so that's all for the classical mirror synchronization I will introduce, and this is the background almost. And anyhow, this is some kind of research that we do before that we are going to the quantum. And so next we will go to the quantum mirror synchronization. For quantum mirror synchronization, first we have this quantum system, and the quantum system is already there. This is a two spaces BGG problem, and so this is our system, and the Hamiltonian is already introduced this two-mode model to describe this thing. What we do is just to rewrite this Hamiltonian like this one. So this is two Hamiltonian system, and this is a coupling. And you will see here the coupling is introduced because it's different atoms, the different atoms of different spaces is interacting each other. So here it is. And we want to show quantum mirror synchronization. And quantum mirror synchronization is a quantum dynamics. So what we need to do is to show the quantum dynamics. What we mean by the quantum dynamics, of course, we all know what this means by the quantum dynamics. It is the Schrodinger equations. So what we need to do is to just solve the Schrodinger equations. And this is it. And also, our system is a Hamiltonian system. So it's a closed and conservative system. And we need to emphasize this kind of evolution for this solving this Schrodinger equation is a unitary evolution problem. So it's just a unitary evolution problem. And to solve this unitary evolution problem, we have two ingredients. The first ingredient is that we need to know the spectrum. So first we have to calculate the eigenenergies for this Hamiltonian. And this calculation is done by the numerical diagonalization of the Hamiltonian that we showed before in the Fock space. And this Fock space is determined by how many particles that we are considering for our system. So it's NA plus 1 multiplied by NB plus 1. This is the dimension that we use. And also, we have to choose our initial state. Of course, the initial state should be the Bose-Einstein condensate state. So there's no problem of that. And this is our state. We choose it. And in the evolution, in the dynamical evolution, what we solve is this n-particle state in a Fock space. So we get this evolution already. And so next, we want to show mirror synchronization. And we've already know, for mirror synchronization, we should draw some Phys picture. But for the quantum dynamics, there is no very easy way that comes to us, tell us what is the phase space. And so we have to find a way to show this phase dynamics. What we did is we defined a pseudo-spin operators for each of the manifold system, the quantum system. And this pseudo-spin is defined as this one. This is for A, and it has 3 terms. And Gx, Gy, and Gz as corresponding. And for B, it's also 3 terms. So here, in principle, we have a phase space in 3-dimensional. It's different compared with the classical one. Because classical, you have a pair of conjugate variable. So it's 2-dimensional. What we are showing in this picture is what we showed for the mirror synchronization. And what we're drawing in here is the expectation value of this Gx and Gy and Gz for each of the A spaces and B spaces. The different color is for the different spaces we are considering. So there are 3 different curves, 3 different figures. These 3 different figures corresponding to different coupling strings. And we are increasing these coupling strings. And this one is for 0 coupling. And this is what we call mirror synchronization. Of course, here is already the quantum mirror synchronization. So this is a picture that we can show for the quantum mirror synchronization. But you may ask me that we have many different ways to represent this kind of dynamics, of course. So just showing this is not enough to show its mirror synchronization. We have to calculate another thing that to make sure this is something that really mirror synchronization. And what we can compare is that this energy. And we did the calculation for the energies. Because we've already tell you that for the mirror synchronization, it's like a demixing to mixing transition for the energies. So this thing can be easily calculated, and we calculate that. And this is an energy calculations that we've done. And here we show the average energies already. So separate curve, it means not mirror synchronized. And together, when the curve is together, it means already mirror synchronized. And also here, the inset is also showing the energy evolutions. And here we choose one for non-mirror synchronized is like this. And another one for mirror synchronized is like this. So anyhow, that we can show that for mirror synchronized state, this energy of the 2 spaces is getting fully exchanged already. But for the quantum dynamics, we will notice that this energy exchange sometimes is dead. And I don't show it further because it can revivals. So the energy can start fully exchange in another. And also, to compare this calculation for the energy and averaged energy, you will notice that here, for the quantum mirror synchronization, it is not a critical transition anymore. A critical transition should be like this one. It's a sudden jump. So, and we testify that and do more calculations, and we find actually this is not a critical transition. It's more like a crossover behavior from non-mirror synchronization to mirror synchronization. So this is some prominent difference compared with the classical mirror synchronization. And also here we show the temporal evolution. And what we calculate is the same quantity, is the population balance that we can do. And this one is for non-mirror synchronized states. And you will notice that for different spaces, this population balance is apparently not related. But for mirror synchronization, this is the calculation for the temporal evolution. And you will notice that it is apparently correlated. And more than that for this kind of dynamics that we've known for the quantum dynamics, it's called collapses and revival. This is collapses and revival dynamics. And we notice that when it reaches mirror synchronization, this collapses here and revival here, this time scale for the quantum dynamics is actually synchronized. So this time scale is the same for the two spaces. So we've already said it is correlated, so we don't have to really to jump to some phase dynamics calculation, so we didn't do the phase dynamic calculation now. And what's more, that for the quantum dynamics, we can show the quantum correlations. And here what we show is for the calculation of the fluctuations. This fluctuation is a particle fluctuation of the atoms. And this calculation is done by doing this calculation. And also here are different figures. And different colors for the different spaces. And for non-mirror synchronized state, you will see these two curves completely separate. So they are not correlated. But for mirror synchronization, these two curves is completely correlated. And you will notice that it's like, at first it is like an antiphase synchronization already. And here is, if we zoom in, you will notice it's like an in phase. So basically we see sometimes it is antiphase and sometimes it's like in phase. And this is for the fluctuation of the two spaces. And also we can show the many-body effects by tuning these particle numbers that we can calculate. And here we calculate for three groups. One is for 20 particle numbers for each of the spaces, and another is for 14, and the third one is for the 16. And also there are two different figures. One is for the mirror synchronized, another is for the not mirror synchronized. And so from this picture, you can also show the quantum correlations is built up for this mirror synchronization. And also for this many-body effects, when we increase these coupling strengths, you will notice this revival time is getting bigger and bigger. And when this n goes to infinite, it means this thing can go to infinite. And this is some limiting case for the classical dynamics. So for the classical dynamics, there is no revival dynamics. So it's corresponding to this revival time is going to infinite. And also, I forgot to tell you what I'm calculating now. Is this calculation that we did for the one-body density matrix. And from this one-body density matrix, what we get is for some quantity to measure the condensed fraction. This condensed fraction is tell us how many particles stay in both uncondensated state in this time of evolution. Because at first it's a coherent state, it's all condensed. But in the time of evolution, it is not. So this is the quantity, the physical quantity that we calculate here. And this is the last result I will talk about. We also did the entanglement entropy. And this entanglement entropy is telling us quantum correlations between A spaces and B spaces. So what how we did this entanglement entropy is that first, we trace out the A system from B system by calculating by getting this reduced density matrix, and then we do a calculation for the von Neumann entropy, and this is a von Neumann entropy, this S. And this lambda is an eigenvalue for this reduced density matrix. And here you show that, here I also show two different figures. And one figure is for non-mirror synchronized state, and another one is for the mirror synchronized state. And you will notice that for mirror synchronized state, this S is larger compared with non-mirror synchronized state. But anyhow, I mentioned before, this transition, when we tune in this coupling strings, this UAV is a crossover behavior. So there is no sudden jump of the energy and this entanglement entropy that we can tell. But anyhow, we show that for mirror synchronization, this entanglement is bigger compared with non-mirror synchronized state. And the summary. The first is a big message that is the title. Is mirror synchronization is no going quantum. And I hope that you've already believed me that actually the classical mirror synchronization is really going to be quantum. And the second is for the comparison of quantum mirror synchronization to the classical mirror synchronization, is that we find even in the temporal evolution, we've already seen the signature for synchronized dynamics. And this quantum collapses and revival dynamics is really getting synchronized already. And also, by showing the quantum correlations, and you will notice that the synchronization dynamics are more obvious in the quantum mirror synchronization compared to the classical mirror synchronization. This thing goes to more general, is that for the quantum system, it might be much easier to reach synchronization compared with the classical one. And the third is that we calculate the entanglement entropy. And there's quantum manifestations of this synchronization with this quantum entanglement. And there are two references, and this one is for the quantum mirror synchronization, and another one is for the classical mirror synchronization. So there are two parts of this research using this hash code system, this boson-Josephson junctions. And thank you.
Any questions or comments? Emilio?
I'm trying to understand the nature and the generality of this transition from two separate phase spaces to one. Is this usually you have two Hamiltonian with 2 degrees of freedom typically when you make them to interact? I don't see this is the general thing that happens. The general thing that happens is that at some moment the periodic or quasi-periodic behavior will give rise to chaotic behavior. Separatist sclerosis, typically you have chaos, not more periodic solution. But in all the plots you have shown, everything was either, in the classical case, was either periodic or quasi-periodic. So is this, what is special to this? Which kind of systems are they supposed to have this kind of transition?
Yes, and this thing I didn't comment is that the periodic motion is only for the initial state, their coupling. If you're tuning this coupling strings, it's always quasi-periodic. And it is true that this separatic crossing is very related to the chaos, because there is a kind of chaos called separatic chaos. So why our system is not showing some prominent feature for the chaos is because we choose the initial conventions carefully. If in general cases, sometimes we just choose randomly. When this goes to the separatic crossing, is always something chaos we have. So that's true. And the dynamics that shown here, most of them is quasi-periodic for the classical mirror synchronization.
Then even in that case, you are showing only the cases in which the initial conditions led to positive.
Yes.
In the quantum, do you find something which is different from what you have shown?
This is what we want to do because we want to do quantum chaos. So I have no comments now.
Any other questions or comments?
In the last letter you showed, so you can clearly see the Rabi oscillations at the beginning of your time traces. Can you go back to the definition?
Which one?
Further back? Here. Right. No, not so far back, like this.
This one?
the second or third last slide.
Oh, sorry.
So here, for example. So here in the beginning, so you plot this over the Rabi frequency. That's the Rabi frequency of the interaction, no?
Yes.
So then you see here the oscillations of with the time scale of the Rabi frequency at the beginning.
Yes.
And then you get a change in frequency. You have the revival peaks, and inside the revival peaks you have a very different characteristic frequency increase. Do you know where this is coming from?
What kind of peaks are you mentioning? Is
So you always have this transient dynamics between the two different
Yes.
coupled species
Yeah.
with the characteristic frequency of the Rabi oscillations.
yes.
And then you have these revival peaks. And then it seems to me you have much faster dynamics. And I don't quite understand where this other time scale is coming from.
This I have no answer to say.
Further questions or comments? Just a curiosity, there are already experiments with the three Josephson junction, Bose-Einstein synchronization.
No, till now there is only a single species BGG, but apparently for the experiment, this thing is already durable, but they didn't do the experiment for this much complicated system. So it's possible that in the future this thing can be tested for two spaces BGG, because the experiment is here.
And is there any possibility of synchronization measure also for different coupled systems, or is always only for identical systems?
It can be different systems, but it is not mirror synchronization, because mirror synchronization must be identical. But for the collective dynamics, this kind of revival, this thing can be non-identical. I test that. For non-identical system, this thing is also there.
So if no further questions, you can just thank